All right, so we are on page 301 in our notes packet. We should be following along and taking notes. Now, before we do that, you do not need to write any of this down. I just wanted to review because this is our first notes for the second semester. So from first semester, I just kind of wanted to quickly review, right? That, the big thing we talked about for the majority of the semester was derivatives, right? And so if I took the derivative, let's say 3x to the fourth, that was 12x cubed. Derivative was our instantaneous rate of change. Right, we also had average rate of change and other types of rate of change, but generally the derivative at a point was our instantaneous rate of change, and on a graph it was the slope. Right, then towards the end of first semester we also added in the antiderivative, right, the integral. So let's say I did the integral, actually let's use 12x cubed with respect to x dx, right? Instead of multiplying and subtracting by 1, we do the opposite. So we add 1 and divide. So this would be 12x to the fourth divided by 4, and we needed to add on that plus c, which would be 3x cubed plus c. And so we can kind of see that taking the derivative, taking the integral, goes backwards, they're inverses, right? You do need to be careful about the plus c if we have no limits on our integral, right? That's a general integral, and that was really the majority of first semester. Now we are going to add this into our notes. What we did also do, and we're going to be talking about particle motion here. So that's when we have our position, velocity, and acceleration table. And so first semester we really focused going down the table, which was taking the derivative. And so now we're going to also add in going back up the table, which will be taking the integral. So the first thing, and I'm actually going to change, if you want to do this as well, I'm going to change these p's to x's. A lot of the more recent AP questions use x, so I'm going to use x. So v of t, the integral of from a to b of v of t dt is equal to the position of b minus the position of a, right? This is the fundamental theorem of calculus, right? Remember, FTC was basically the integral from a to b of little f of t, actually, was equal to big F of b minus big F of a. And big F is the integral. Well, if we kind of look, if we start at velocity on this table, right, if we go up 1, right, we would need to take the integral. And so that's where this formula comes into play. Now, I like what's called kind of my alternate method of FTC. And this works really well for a lot of problems. And what we do here is we just add f of a to both sides. And so that's f of a, plus the integral from a to b of f of t dt equals f of b, and then I just switch sides. So I write f of b equals f of a plus the integral from a to b of f of t dt. So this is kind of like, I call that the alternate FTC, and I really like that. So I want you to add that in for this equation, and that's going to basically give us x at b, like x at some new position, is equal to x at a, meaning our starting position, plus the integral from a to b of v of t dt. So essentially what that tells us is, if we take the integral from a to b of v of t and we add on the starting position, that gives us our final position. And so what that really tells us is that this integral is the change in the position, right? Because that's going to be the change in the position. We're going to add on our original position, and that's going to give us our new position. And that's actually exactly what the second tab says, right? Is that the integral from a to b is the net distance. That's, net distance basically means our change in position, which would also be our displacement. And then the third one is this absolute value from a to b of, or the integral of the absolute value of v of t from a to b. And that gives us the total distance, right? The total distance. So just a quick reminder is if you had some kind of a particle, we went to the right, then to the left, then to the right, then to the left, and we ended here. This would be our displacement, right? And then the entire path going back and forth would be our total distance, right? So kind of adding up all of those. And I'm going to say like the distances, right? So the distances, meaning it doesn't matter if it's going left or right, we're just going to call it positive. That's going to become our total distance. All right. So really, I know it's kind of hard to look at these three rules and then really understand it. So we're going to do some problems, some examples, and hopefully that starts to solidify it. So first question, we have the velocity of a particle moving along the x-axis, and we're given that its velocity is 3t squared plus 6. So they say if the position of the particle at time 4 is 72. This is kind of an initial force. It doesn't matter that it's time 4 and we're going backwards to time 2. It's an initial, condition, right? It doesn't have to necessarily be the initial starting point of the particle. It's an initial condition. And so anytime we have that initial condition, that's going to be like our x of a that we were talking about. Whatever we want, right? This is what we want. That's always going to be our x of b. So I like to use that alternate form, which was x of b is equal to x of a plus the integral from a to b of v of t dt. So that's going to tell us x at 2 is equal to x at 4 plus the integral. Now, a is the bottom term, b is the top term. It doesn't matter that 4 is bigger than 2, right? You just have to match up the spots. So the integral from 4 to 2 of v of t, so 3t squared plus 6 dt. Now, if you want to change the endpoints, we can change this positive sign to a minus sign. I'm not going to worry about that. I'm just going to go ahead and the negative sign will kind of work itself out. So x at 2, we don't know that. X at 4 was 72 plus, and then I'm going to put this in parentheses, 3t squared over 3 is t cubed plus 6t from 4 to 2. And it's important to put this in parentheses because we don't want to add the 72 in there. All right, this is going to give us 72 plus the integral. We're going to plug in 2, so that's 2 cubed is 8 plus 6 times 2 is 12 minus 4 cubed is 64 plus 6 times 4 is 24. That's going to be 72 plus 20 minus, that's 88. All right, that gives us 92 minus 88, which gives us x of 2 is 4. Right. What is the total distance the particle travels from 0 to 7? Now, honestly, I know I said on here this is a non-calculator active question. I have very, 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 very rarely seen anything like this in a on a non-calculator. It's 99% of the time a calculator question. So I'm going to show that first because honestly, on the AP test, I've never seen them ask us to do this by hand with something this complicated. This would 99% likely be a calculator question. So basically what we would just do is that the total distance formula is the integral from, in this case, 0 to 7 of the absolute value of v of t dt. You would need to write this down, but then from there, you could just move over to your calculator. So it's up to you if you want to write out the 3t squared plus 6. You could write that instead of v of t, but it's very important to write that line, right? If you don't write that line, you're not getting credit. So moving over to our calculator, I will kind of show this because it's been a while. Right to the left of the book is this button here. We got our integral symbol with our two endpoints, and we're going from 0 up to 7. And then again, on that same button to the left of the book is where our absolute value sign is. It's in this top right. And then we had 3t squared plus 6, I believe. And then we need to put in dt. And that gives us 385. Right? And so in all likelihood, that would be all we have to do. 385, box it, and we're done. Now, in the very, very off chance that you do get this as a non-calculator question, what you would basically need to do is kind of really have a good, solid understanding of the graph and the fact that, basically if I have some graph here and we're going from, this point to this point, this is the area here. It's positive. All of this area is negative, but it's going to turn positive when we take the absolute value, and that area would stay positive. So in this case, because we do have 3t squared plus 6, that is a pretty basic graph, right? So 3t squared plus 6 is a parabola, but it shifted up 1, 2, 3, 4, 5, 6. And so actually what you can kind of see is that this is always positive. And so if you do have a graph that's always positive, 1, 2, 3, 4, 5, 6, 7, wherever this ends up being, what you'll notice is this area under this curve will be always positive. So it doesn't matter. What that means is that the integral from 0 to 7 of the absolute value of v of t will just end up being the integral from 0 to 7 of v of t, because the graph is always positive. So in this case, we could just do this problem by hand. 3t squared plus 6. Right, the integral of 3t squared is t cubed plus 6t from 0 to 7. That gives us 343 is 7 cubed plus 42 minus 0. And that gives us 385. All right, number 2, we have another question where they're giving us a velocity, right? V of t is 0.5 e to the t times t minus 2 cubed. And this one is a calculator question. So I do want to practice writing down what we need to write down on the FRQ. So they tell us if the position of the particle at time 1.5 is 2.551. Again, this is an initial condition. Okay, that's an initial condition. So that's going to be like our x of a. What is the position when time is 3.5? This is what we want. We want this position. So that's going to be x of b. So all we have to write down is x of 3.5 equals x at 1.5 plus the integral from 1.5, right, that's that one, to 3.5 of v of t dt. You do not need to write all of this in there because it was defined for us. You also don't even need to ever write 2.551. You can just write x of 1.5, again, because it was defined for us. So this is actually the only thing you need to write down, and then you just type into your calculator. So into our calculator, what we're going to do is just type in 2.551 for that x of 1.5. Plus the integral, same, from, this was 1.5 to 3.5. All right, and then we type everything in, we hit enter, we get our answer 18.47019. I want to go out to at least 4 decimals, and we will just write that down. And that is our answer. Okay. The second one, what is the total distance of our object? So for our total distance, the only difference now is that we're going to add on that absolute value. So we would say that the total distance is equal to the integral from 1 to 5. And there's on total distance, by the way, we do not care about the starting value. We don't care about what x of 1 is or the initial condition, because total distance is just how far did we go between 1 and 5. It doesn't matter where we started off at. It just matters how far we traveled. Whereas on, when we want the position at 3.5, it does matter the position we started with. So this is going to be the integral of the absolute value of v of t dt from 1 to 5. So that's all you need to write down. Then we can type this into our calculator. So coming back over to our calculator, what I will do is just kind of come up here, highlight this, then I'm going to select this part, delete it, and then you can actually just, come here, and if you hold down shift right here, right, and you just hold down shift and you highlight all this, you can, once it's highlighted, go to this button to the left and press the absolute value, and it will turn all of that into absolute value. We do need to change our endpoints because this changed from 1 to 7. No, 1 to 5. And then we get 913.0670 for our answer. I do like to add that 0 in because that is the 4th decimal, 0, and that indicates that it will keep going, right? All right, next up, we have the graph of the velocity. And so instead of having an equation, we're going back to graphs. And so we want to make sure we remember that derivative is our slope and an integral is our area under the curve. So we know that the position of the particle at time 8 is 12, right? That means x of 8 is equal to 12. We want to use the graph to answer this question. So we want to know what is the position at time 3. That's going to be our x of b, right? This was our x of a, was the 12. So we want to basically set up our same equation we've been doing. X at 3 is equal to x at 8 plus the integral. That's our a. So from 8 to 3 of v of t dt. Now, this is where you do need to realize that 8 is a bigger number, so we are going backwards, right? So we're kind of starting off at 8, we're finishing at 3. If we're going backwards, what that means is even though normally this would be negative, because we're going backwards, that's going to be positive, and this is going to be negative. If you don't want to deal with that, another thing you could do is you could just do x at 8 minus the integral from 3 to 8 of v of t dt, and if you do that, then you'll be going forwards, right? And so this will be positive, this will be negative, but it'll be taken care of because of that minus sign. I personally don't like to do that because if you don't put a big parentheses around everything, it kind of messes you up. So I just like to say, if I'm going starting at 8, I just flip all my signs. So that's what I'm going to do. So we're going this way. So this first one is a triangle. And because it's below the axis, but we're going backwards, that's going to be positive. I'm going to put a positive here and a negative here just so I remember that. So this is going to be plus 1/2. The width of that triangle is 2, and the height of that triangle is 2. So 1/2 times 2 times 2. And then minus, right, because we said this next one's going to be above. And I'm going to split this one into 2 shapes, a triangle and a rectangle. And so it's going to be, for the triangle, it's going to be minus 1/2 times the width is 2, the height is 5, and then again minus, for the rectangle, the width is 1, and the height is 5. So this is going to be 12 plus 2 minus 5 minus 5. That gives us 14 minus 10, which means that x of 3 is 4. Right, what is the acceleration when the time is 5, right? Not the position, but the acceleration. So we want to kind of go back to that chart, position, velocity, acceleration. We have velocity, that's what the graph is. How do I go down? Well, to go down the chart, we take the derivative. How do I do a derivative on the graph? That's the slope. So this is a fancy way of asking what's the slope at time 5. So I'm going to write a of 5 is equal to v prime at 5, which in this case is the slope of this, right? That's, if we kind of look here, we're going down 5, right 2. So that's negative 5 over 2. Right, what is the total net, or sorry, what is the net distance? The particle travels from 0 to 10. So net distance, we do include negative signs, right? Net distance is kind of like displacement. So what we're going to do, I'm going to erase this stuff, is we want to basically, if I want the net distance, that's the integral from 0 to 10 of v of t dt. So that's every single one of these areas. So this triangle, this rectangle, this triangle, and then I'll group this all as one. So this is going to be, we already kind of did these, 1/2 times 2 times 5, plus, now this is going to be 2 times 5, plus another 1/2 times 2 times 5, and then minus, for this final triangle, that is a distance of 4, so 1/2 width of 4, and then a height of 2. So we can see that that cancels, and that cancels. So this is 5 plus 10 plus another 5 minus 4. That's 20 minus 4, so 16. So our net distance or displacement between 0 and 10 is 16. Now, what is the total distance? The difference on total distance is essentially that now we are going to take the absolute value of the integral. So from 0 to 10, the absolute value of v of t dt. And what that essentially does is it just makes sure all of these areas we're doing become positive. So I can just reuse those numbers, but just make them all positive. So 5 plus 10 plus 5 plus 4, and so that ends up being 24. Okay. And so we've done an equation, we've done a graph, we also want to be able to do these with a table. So we are given a table with velocity, and we're first asked, what does the value of the integral from 0 to 18 of v of t represent? This is kind of coming back to making sure we know these three things, right? And so just the integral, that's our net distance or our displacement. We can use either word. I like displacement a little bit better, or change in position is good also. Change in position is actually really solid, because if we just think position, velocity, acceleration, right, going up the chart is the integral. And anytime you're using integral in a sentence, it's always good to just say the change in whatever it becomes. So I like that one. So I'm going to say the integral from 0 to 18 of v of t dt represents the change in the position of, and I'm going to kind of use this, the particle along the x-axis. And then I want to always put a comma and then say in whatever units it is. Now I had meters per second. Whenever you go down the table and take the derivative, you add on a unit of per time. And conversely, whenever we go up the table for our units, we chop off a unit of time. So what's going to happen is when we basically take the integral, we're going to chop off that per second. So this is going to become in meters, right? And that's going to be what position is measured in. And then from 0 to 18, those are times, so that's seconds. And this is very, very good to kind of memorize that as a sentence starter. All right, next up we have using a left Riemann sum, right? So using a left Riemann sum of subintervals, six subintervals, estimate the value of the integral from 0 to 18. So we're going to say the integral from 0 to 18 of v of t dt is approximately, we're doing a left Riemann sum, so that's a width of 3. We're going to multiply by the left part. Then plus from 3 to 6, that's again 3 times 2.7. From 6 to 9 is also 3 times 2. Looks like these are all going to be 3. Plus 3 times 1.3. Plus 3 times 1. And then plus 3 times 1.7. We do want to just kind of double check 1, 2, 3, 4, 5, 6. That looks right. Now this we can just do on our calculator. This with these decimals, this would not be a non-calculator question. And so we type all of that in and we get 33. We're going to add the units, and those units would be meters, right? Because we're taking the integral of a velocity, we chop off the per second. All right, using a right Riemann sum of 6 subintervals of equal length, estimate the value of integral of 0 to 18. So same thing, but now we're just doing a right Riemann sum, so we're just kind of reviewing those Riemann sums. And this is going to be all of those same 3's, but now 3 times 2.7, 3 times 2, 3 times 1.3, 3 times 1, 3 times 1.7, and 3 times 2.1. So I'll write that out really quickly for us. And then to type that into our calculator, we can actually just kind of come back up here and we can delete the first one, right, the 3 times 2.3, and we will then replace that at the end with the new one, 3 times 2.1. So we get 32.4. All right, and then the next one we're reviewing midpoint Riemann sum. So with our midpoint Riemann sum, and actually, you know what, I'm going to skip ahead. I'm going to do E first because that's going to keep the 3's. So for our trapezoid, we would do the integral from 0 to 18 of v of t dt is approximately, so each one of these, we're going to do 3, and then we're going to multiply both of them, divide by 2. This is going to kind of be 3 times, the first one was 2.3 plus 2.7 divided by 2, then plus 3 times 2.7 plus 2 divided by 2, plus 3 times 1.3, 2. 2 plus 1.3 divided by 2, plus 3 times 1.3 plus 1 divided by 2, plus 3 times 1 plus 1.7 divided by 2, plus 3 times 1.7 plus 2.1 divided by 2. Right, and so that's our trapezoid, right? Each time we're multiplying, the width, which was, say, 3, times both of those, the left and the right, divided by 2. So you'll go ahead and type that into your calculator, and you should end up with an answer of 32.7 meters. There we go. All right, now coming back to our midpoint Riemann sum. So on our midpoint Riemann sum, they said instead of using 6 subintervals, we're only going to use 3, and this is very common. So now we're going to use 3 subintervals, so it's going to be from 0 to 6, that's a width of 6. We're going to multiply by the middle. Then from 6 to 12 is 6. We're going to multiply by the middle. And from 12 to 18 is again 6. We're going to multiply by the middle. So this would be approximately 6 times, what was the first one, 2.7, plus 6 times 1.3, plus 6 times 1.7, and I'll just let you guys type that into your calculator. And you should end up with a value of 34.2 meters. All right, and then finally find the average acceleration of the particle from 3 to 9. For what value of t in the table is this average acceleration approximately equal to v prime of t? So again, we have position, velocity, acceleration. We have velocity. If we want the average acceleration, that's the derivative. So it's like the average rate of change. So what we're going to basically say is that the average acceleration is approximately equal to v of 9 minus v of 3 over 9 minus 3. That's our average rate of change formula, right? y2 minus y1 over x2 minus x1. So v of 9 is 1.3 minus v of 3 is 1.7, I believe. No, 2.7. So 1.3 minus 2.7 divided by 9 minus 3. I like to leave that y2 minus y1 over x2 minus x1. Then you'll type that into a calculator, and we get negative 0.23 repeating. And for our units, this is going to be meters per second squared, right? I said when we go down the chart, we add on a per ton. So we had meters per second. Now we're going down the chart, right? That's going to be meters per second squared. Now it says For what value of t in the table is the average acceleration approximately equal to v prime of t? And this one is a little bit tricky. And so if we kind of come back up to this table, it's not quite clear where this value is. And I really think this is way too hard of a question. I don't think that they would say that. I think they might say like, must there be a time like that? And then, you know, we would say basically like by MVT, there must be a value of the acceleration equal to negative 0.233 meters per second squared for 3 less than or equal to t less than or equal to 9, because v of 9 minus v of 3 over 9 minus 3 equals negative 0.233, right? And you know, you might add in that it was continuous and differentiable or something like that. Now, if you're, you know, actually really want the answer looks like it might be t equals 6. And that's because if you kind of look at t equals 6, it goes from 2.7 to 2, that's down 0.7, and then it's over 3, down 0.7 over 3. And so if on a calculator you type in negative 0.7, right, that would be the rise, right? So negative 0.7 divided by 3, you do get that same answer. Again, I don't really think that's a fair question. All right, so our homework is going to be the day 52 homework. We have a graph question. So that graph question, you'll want to kind of go back up to our graph example. And then we will have another graph question. And then we have a table question. And that's it. We do not have for this one an equation. I do also want you to try this 2001 problem 3, and you can Google this answer, and after you try it, and then kind of grade yourself, and then again the 2002 one as well, and then you can Google that answer as well. This one is a calculator question for sure. The first one looks like it was a calculator question as well, but you may not need it as much. But the second one, you'll definitely need the calculator on, right? And then if you want to try to watch this video before tomorrow, then, sorry, this next video for page 309 before tomorrow, then you can work on the questions, the homework during class. That's totally up to you.